Welcome to TechnoSapiens.
Welcome to today's explainer. I am so incredibly excited to get into this one with you today because we're going to look right past the drywall and uncover the invisible, literally everyday physics happening inside our walls right at this very moment. Seriously, think about it. Have you ever noticed a plug feeling just a little bit warm after running a space heater? Or maybe you've wondered what is actually going on inside those thick cables running all throughout your home? Well, we're going to break all of that down today. Section 1. The electrical heating mystery. Okay, let's dive into this. We are totally surrounded by wires every single day, right? They're powering our lives, our phones, our entire modern world. But that brings us to a really simple everyday question. Why does an electrical wire actually get hot when current flows through it? The answer unlocks a pretty fundamental truth about how electricity interacts with our physical world. Because you see, it's not just pure magic effortlessly flowing through a hollow tube. There's a very real, tangible physical process happening in there. Section 2. Zooming in, electrical resistance. To truly understand what's causing this heat, we're going to shrink way down past the copper and the plastic coating, right to the microscopic atomic level. This brings us to electrical resistance. It's the property causing moving electrons to collide with atoms in the wire's material. The absolutely crucial thing to wrap your head around here is that electricity isn't just this unobstructed river flowing freely. Not at all. Every single wire has some electrical resistance built right into it. So as those electrons try to move through the wire, they aren't just gracefully gliding along. They are literally crashing over and over into the very atoms that make up the wire's material. It's essentially a microscopic obstacle course. And because of that intense obstacle course, these collisions convert energy into heat. Every single time a moving electron smashes into an atom, a portion of that electrical energy is transformed. It doesn't just disappear into thin air, it becomes physical heat. So naturally, the greater the current flowing through that wire, the more electrons are moving. More moving electrons means more collisions, and ultimately a whole lot more heat is produced. Section 3. The power equation. Now, what's really interesting about this slide is how we can take all of that atomic chaos and perfectly describe it using math. P equals I squared R. I know, math on a screen, but this isn't just a boring equation, it's actually a highly dramatic multiplier. In this formula, P is the power, which in this context means the heat being generated. I stands for the electrical current, and R is that electrical resistance we just talked about. But here is the absolute most vital part of this whole equation, the tiny little 2. The current is squared. Because that current is squared, this relationship isn't just some simple straight line. If you simply double the current flowing through a wire, the heating effect doesn't just safely double along with it. No way. It exponentially quadruples. It becomes 4 times greater. That squared factor means heat scales up incredibly fast when you start pushing a bigger load through the system. It's a massive escalation. Section 4, the danger of overload. So, when we zoom out from the math and look at the macro consequences, that exponential heat growth turns into a tangible, real-world threat incredibly quickly. And this brilliantly illustrates the exact step-by-step chain reaction of an electrical disaster. Think about it like this. Step 1, you have a wire that's just too small for the load it's carrying. Thanks to our I-squared math equation, we immediately hit step 2. The temperature of that wire rises really quickly. It's generating way more heat than it can safely dissipate. This rapid heating pushes us right to step 3. The insulation, that protective coating designed to keep the electricity safely contained, it gets damaged or it just melts entirely. And when that crucial barrier fails, we arrive at the terrifying step 4, fire. This sequence shows exactly why a wire carrying too much current is so incredibly dangerous. Section 5, built-in protections. Okay, take a deep breath. Because thankfully, smart human engineering steps in right here to stop this dangerous escalation before disaster strikes. Modern electrical systems use a combination of these specific tools to keep us all safe. First up, we use properly sized conductors. This just ensures the wire is physically large enough to handle the electrical load without the resistance generating those dangerous levels of heat. Then we have things like fuses and circuit breakers. These are brilliantly designed protections built right into the system to strictly control excessive current. If the current spikes and that exponential heat threatens to rise, these devices just step in and automatically cut the power. They shut down the circuit completely to prevent that scary chain reaction we just looked at. To wrap things up today, let's hear this fantastic quote directly from our source, TechnoSapiens. The heat up because electrical resistance converts electrical energy into heat, not because it's flowing too fast. I love this because it perfectly busts a really common myth. Electricity isn't some liquid rushing so quickly through a pipe that it causes friction. Nope, it is a constant, microscopic collision of moving electrons and physical atoms where electrical energy is literally converted right into heat. So I'm going to leave you with this. Are the wires in your walls properly sized for the load they carry? It's definitely something to chew on the next time you plug in a heavy appliance or even when you just casually glance at the breaker box in your garage. That invisible physics of resistance is always at work, right there behind the drywall. Thank you so much for joining me for this explainer. Stay curious and keep learning.